So, how is everyone? Like one person. How's everyone? Hello? Some people just logged in and left or what? How are you, ladies and gentlemen?
We are good and how are you, sir?
Okay. Oh, okay.
Oh,
So today we are supposed to have a tutorial. Are you people ready to do the tutorial? Did you go through the? Are you able to produce the solution for the tutorial? Okay, so
yes, sir, we can try.
I just thought that I could give you a little bit more time. Then I think we are also going to have a challenge, a little bit of a challenge in terms of how you guys are going to write. I don't know. So as we are trying to sort out all those problems, maybe we can continue with the lectures. You know what I mean, right? How you guys are going to do the writing, because I want to see how you are solving the tutorials. So one of the students must come and start solving as the other members of the class are contributing. And then I can correct you where you are going wrong and I can advise appropriately. So now the writing will be a little bit difficult, but we'll figure out.
So you mean?
Hello? 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 Hello, there was a question?
Yes, sir, I have a question.
Yes, go ahead.
Yeah, so you mean we'll do tutorials when we open in the first week of November?
Which I don't know whether you manage to do all the tutorials, because I think when you open, we only have a week. In the second week, we are writing the test. So we should just have that in mind. It means that we are going to do the tutorials when it comes. That the following week, you should be ready to write the exam. Okay?
Yeah. Sure. I'll
Hello? Okay, so let us proceed with our class for today. So I think the issues, the other issues, any other business can come at the end of the class. Okay, so I'm saying that today's lecture will be about electric potential. Just to give you a brief background of how we have moved, we started by talking about the Coulomb force. Okay, we said that when two objects, let's say we have a particle and another particle, when two objects are separated by a certain distance, let us call it R, then the Coulomb force, if they are point charges, the Coulomb force, we said that is just some constant, and then Q1, and then Q2 over R squared, where R squared is the separation distance. So we are saying that this is Q1, this is Q2. And by the way, these are just magnitudes, the magnitudes of the two charges, and then this is the separation. So this is the Coulomb force. We went to electric field. We said that actually the electric field is a property of one charge. So whenever you have a charge, that means in all the region around that charge, then you have the quantity that is called the electric field. And then for point charges, the electric field, in fact, we just said that the electric field is the force acting per unit charge, the force that is acting on a test charge. And we say that for point charges, the electric field that is emanating from a certain charge will just be given by K, and that charge over R squared, where R is the distance from the charge to that particular point where you want to find the electric field. Now, we have done these two concepts. This concept, when talking about this concept, that is what brought us into issues of Gauss law, trying to find the electric field using Gauss law. So today now we are going to come to yet another concept that is called electric potential. Okay, so now what is meant by electric potential? In order for us to understand what is meant for by electric potential, let us try to review a bit on the aspect of work. Remember, in first year somewhere there, you learned about work done by a constant force. So I have a question here that I want you guys to answer. And the question reads as follows. The right figures show 4 situations in which a force is applied to an object. In all 4 cases, the force has the same magnitude. The force has the same magnitude, and the displacement of the object is to the right of the same and of the same magnitude. So the question is, rank the situations in order of the work done by the force on the object from the most positive to the most negative. So this is a revision. So we have these 4 different situations. You have an object, then you have a force acting in all these different directions. So we are supposed to rank the work that is done by the force. And then the key word here is that the displacement is in what direction? The displacement of the object is to the right. Okay, so what do you guys think? Okay, so let us give ourselves 30 seconds to figure out what is happening here. After that, I'll expect input.
Since the question is saying that the displacement, the rest, I think B should be the correct answer.
Pardon?
Since the question is saying that the displacement of the object is to the right, I think B should be the answer.
So B should be the answer. Okay, so why did you say B is the answer? What is your analysis?
According to the question, it's saying that in all 4 cases, the force has the same magnitude and the displacement of the object is to the right.
So now the question is rank the situation in order of the work done. So why have you chosen this? Okay, so keep a mental note of this question. I think I'll ask it again.
Personally, I think the answer is E.
Oh, okay. That answer is coming from who?
My answer.
Kenny's answer is B, right? Kenny's answer is B.
E.
No? E. And then Kenny.
E, sir.
E.
Yes.
Okay. And then Kenny?
Yes. Sir, since the displacement is to the right, when you look at the figure number, the figure number 3 there, it shows the direction of the force, which is also to the right. So meaning that one is the most positive. And when you look at figure number 4, you have the force is at an angle. So it's partially upwards and partially right to the right in the direction. So that one.
We have heard your point, sir. Now tell me, what is the equation that we use for work? What is the equation that we use for work? Work is equal to what? The work that is done by a force? The work is equal to what?
It's the force times distance.
Okay, that equation is wrong. It was only correct at grade 12. I don't expect that one at this particular point stage. Is it correct to say that the work is just force times distance? Huh? Huh? Is it correct to say that work is just force times distance?
We might say that the product of forces displacement.
The what? Okay, so the work done is basically the dot product of the net force acting and the displacement. So both of these are vectors. So when we take a dot product, so the work that is done is basically a dot product of the net force acting on the object and the displacement in the direction. Are we together? So no, when you say work is equal to force times distance, this only applies when the force is applied horizontally, like in this particular case, where the work and the displacement are in the same direction. That is the only time when this formula works. But in general, we say the work is the dot product of the force and the displacement. Now, dot product from your mathematics, you know that the dot product is the magnitude of the force and the magnitude of the displacement times the cosine of the angle between them. Are you okay with this formula? Are you all okay with this formula?
Yes, sir. Yes.
Okay. So now let us analyze the situation. So here I'm just saying that the work done is just basically the dot product of the force and the displacement in the direction of the force, which involves this cos theta term. So the most important thing is for us to identify what is our theta. Theta basically is the angle between the force and the displacement. We have been told that, so in these four diagrams, we are trying to analyze the situation. The displacement is indicated by the line in blue. So this is the displacement vector, displacement vector, displacement vector, displacement vector. It is to the right, that's what we have been told. Now let us try by scenario number 1. What is the angle between the force? What is the angle between the force and the displacement in scenario number 1?
90.
90, good. So then what is cos 90? What is cos 90?
Zero.
It's 0. So what is the work done by this force in scenario number 1?
There is no work done.
There is no work. The work done is 0. So scenario number 1, we have established the work done is 0. What about scenario number 2? You see the displacement is in this direction, but the force is acting in the opposite direction. What is the theta? What is the angle between the two? It's 180. And what is cos 180?
-1.
-1. So then what is the work done? It is just equal to the magnitude of the force, the magnitude of the displacement is the minus F and then delta R. So here we have minus F delta R because the angle there is 180. What about scenario number 3? What is the theta? Scenario number 3, what is the theta?
Theta is 0.
Theta is equal to
That should be 0.
What is cos 0?
1, positive 1.
1, positive. So in this case, the work done will just remain to be force times the distance is the one that was mentioned at, where the force and the displacement are right in the same direction. Okay, so we just have the force and the displacement in that. Now, and then what about here, scenario number 4? Scenario number 4, we have just been given a general angle. You see the angle between these, just a general angle where that is equal to theta. So what is the work? Then the work in general is just that for scenario number 4. Okay, so in that case, if you have to plot this on the number line, then which one? You know that the cosine of any angle will be any number between, it will be any number between 0 and 1. Are we together? So if you multiply this by this, you know that this work would definitely be less than this work because you are multiplying by a number that is less than 1. So already you can see that the maximum work that you can have is in scenario number 3. That is the maximum because the theta is equal to 0. There, all the work is actually going, all the force is actually going into doing work. All right. So this one we are ranking from the most positive. So we know that this one will be the first, and then this will be followed by which one? This will be followed by which one? This will be followed by this one because you know that
Number 4.
This number 4. This will be followed by this one. Okay, and then will be followed by which one? On the number line?
Number 1.
Will be followed by 0. We are going to the left of the number line. And then the most negative one will be here. Okay, so now let us ask the question again after this analysis. So then which one is the answer? Which one is the answer? No? The answer is what?
E.
So we can see that the answer here is nothing but E. Okay, so that was just a revision about work. The fact that work can be negative, it can be positive, and it can also be 0, depending on the angle between the force and the displacement. Okay, let us also revise something about potential energy, the relationship between work and the potential energy. To start with, let us talk about the gravitational work. The gravitational work. So consider an object, this object that is here. Consider this object that is here. That is initially at a height, this is the ground level. So this object is at a height initially of y initial, and then finally it goes to a height of y final. Okay, so that motion is happening like that. So that is the displacement. So in what direction is the displacement? Is it upwards or downwards?
Upwards.
It's upwards. So the displacement vector, you can see that it is from here where it initially was to here where finally it comes. So this is the, now what is the force? What is the force that is acting on this object? It is the force of gravity.
Gravitational force.
Gravitational force. In what direction is the force?
Downwards.
Downwards. So the gravitational force, as we can all agree, is basically downwards. So this is the gravitational force. So what is the angle? So we know that the work that is done by the gravitational force, we are calling it WG. So the work that is done by the gravitational force will just be the gravitational force itself, the dot product of the gravitational force, and the displacement. So you know that there is a cosine theta, because of the dot product here, there's a cosine theta that will come into play. So we have to identify what is the angle between the force and the displacement in this case.
180.
It is 180. So what is cosine of 180? It is -1. So you can see that the work, it will be a minus. The force in this case, the force is mg. You understand where the minus is coming from? It's coming from the fact that the force and the displacement are at an angle of 180 degrees. And then the force itself here is mg, which is the gravitational force. And we have this basically is just a displacement. Displacement is given by the final position minus the initial position. So in short, we are saying that this can be written as minus m, and then the y final minus the y initial. So that is basically the work that is done by the gravitational force. So I can actually distribute. When I distribute this negative that is here, I distribute it inside. Then I come up with this equation that is here. Are we all together on the steps reaching this, leading to this equation? I've just distributed this minus sign there. Okay, so in short, what I have seen is that the work that is done by the work that is done by the gravitational force is just mgy and then minus mgf, where yi is the initial position and then yf is the final position. Now, remember again from your first year course that mgy is basically just the potential energy. Remember mgy or mgh. In this case, y is synonymous to h, the height. So the potential energy, we denote it by the letter U. So the potential energy, which is gravitational, is given by mgy. So what does this mean? Mgyi, it simply means that this is the initial potential energy minus this guy here, which is the final potential energy. So the work that is done is just given by initial potential energy minus final potential energy from this equation that is here. Now, you know that when we say the change in a certain quantity is given by the final value of that quantity minus the initial value of that quantity. So the change is given by the final minus the initial. But here what we have is the initial minus the final. What does it mean? That means this is a minus change in potential energy. So here we have found a relationship. We have found a relationship between the work and the potential energy. It means that the change in the potential energy is just equal to the minus of the work that is done by a force. The change in potential energy is basically equal to the negative of the work that is done by that force. In other words, we are saying that when you do work on a system, when a force does work on a system, that work gets stored in that system as potential energy. This minus here is telling us that that work is actually stored. That's what the negative signifies. Any questions before we go further? The relationship between work and potential energy. Any questions? Is it clear?
Yes, sir.
Okay, so this formula here, keep it in mind. We are going to use it several times. The relationship between the potential energy and the work done by the force. So just to remind ourselves also some other points, the work done by a conservative force on a particle moving between any 2 points is independent of the path taken by the particle. So actually, by definition, a conservative force is a force where the work that is done by that particular force is independent of the path taken. And what does that mean? From this scenario here that I had shown you, from this scenario that is here where the object is moving, here the object moved from here, from this initial point directly to that point here, okay? So this object could have used different paths. Maybe it could have used, it goes somewhere here, and then it comes back here. Or it could have used from here, it goes somewhere here, it comes here, okay? So it simply means that as long as the initial point and the final point is the same, the work done by a force that is conservative is the same. So a conservative force by definition is a force where the work that is done by it does not depend on the path that is taken. All right, the other point that we can note is that the work done by a conservative force, you know, gravitational force is one of the conservative forces, actually. So the work done by a conservative force on a particle moving through any closed path is 0. So what does that mean? Assume that the work, the object, when going here, it takes up this path, it comes here. And then again, this is the first part. And then secondly, you move the object again from where it was back to its initial position. So what does it mean? It means that when going here, it means that you are doing work. It means that that work is being stored in that system. And then what about as it, so it means that when it goes to that position, it means that it has got a bigger, but its potential energy has increased. What about when taking it back? You can see that the potential energy is reducing. And then when it reduces by the same amount, since the final and the initial positions are the same. So this positive work that is done, which is the potential energy, will be cancelled by the negative work here, which signifies a reduction in the potential energy. So that as long as the path is closed, and the force is conservative, then the work that is done is equal to 0. Any questions? Any questions? Okay, no questions. Thank you. So now, in this, what we are doing, we are trying to revise on something that is familiar so far, which is gravitational potential. We have talked about work that is done. Okay, the work that is done is stored as potential energy. So in order for us to calculate the potential energy, it is just the same as calculating the work that you have done on the system, and that will be the same as the potential energy that you have stored in that system. Okay, and then we have also identified that this force is conservative. Now, what has this got to do with the electric fields that we are talking about? Okay, so from the previous slide, we have said that the change in the potential is equal to the minus work that is done. Okay, and we have also established that the work done by we can say that the electrostatic force is just the force between charges that are stationary. The electrostatic force is also an example of a conservative force. It is just like gravity. It is a conservative force where the work that is done is independent of the path. Now, let us try to look at the work that is done. So, for instance, let us say you have this charge. This charge is producing an electric field. This electric field is shown in red. So, this point charge is producing an electric field radially outwards. So, when you place another charged object within the vicinity of this, or when you place another charge in the electric field of the first charge, then you expect a force. You know, in this blue line here represents a force. So you expect a force to act on it. And then when the force acts, it is going to move that particular object by a certain displacement. It's going to displace the second particle because of that force. So you see that there is a force, and then that force is accompanied by a displacement. So what does that mean? It means that there is some work that has been done by this electric field. And that work is basically the dot product of the force and the displacement that has been made. Now, what is this force? This force, how can you relate this force to the electric field? Remember, this force is just the product of the charge and the electric field, if you remember where we are coming from. So this force is nothing but the Q, which is the magnitude of this charge, and the electric field within which it is placed. And then this is the force, and then you are finding the dot product of this force with the displacement. Now, can someone tell me what is the angle between the force and the displacement in this case? What is the angle between the force and the displacement in this case?
I think the angle is 0.
The angle is 0. The angle is 0 because you can see that the force is in the same direction as the displacement. Okay? So the cosine of the angle, it will just be cos 0, which will just be equal to 1. Now, let us try to also look at if I was supposed to do what? You know, initially, this charge here had an initial potential energy here. And then when I move it to that direction, it has a final potential energy. So then how can you connect the potential energy and the kinetic energy? The potential energy and the work that has been done. We can say, from what we have learned, we can say that the work that has been done must just, the work that has been done by the electric field must just be equal to the minus of the change in the potential. Am I right?
Yes.
Okay, the work that has been done by the electric field is just equal to minus the change in the potential. Okay, so we are making progress now. Let us look at another scenario. Another scenario. If this charge here is moving very, very, very slow in such a way that it is moving with a constant speed, then you expect that the external agent must also apply a force in this direction, which is almost the same as the force. You remember from Newton's first law, it means that for an object to move at constant speed, then the net force must be equal to 0. So it means that there must be an applied force on this. In short, maybe let us look at it from this perspective. If this charge here is moving very, very, very slowly, we say that it is moving quasi-statically. If the charge is moving quasi-statically, what does it mean? It means that the force that is acting on it in this direction must be equal to the force that is acting on it in this direction. So where is this force? Where should this force come from? It must come from the external agent. It means that the external agent must also push this in this so that it moves very, very, very slowly in such a way that it is moving fast. Okay. So we ended on the note that we are talking about quasi-static motion. We say that the force that is applied by the external agent must be in the opposite direction to the force that is being applied by the electric field, and it must also be equal in magnitude. So it means that now, if you look at this force that is being applied, we call it the applied force. Now, this applied force, what do you think is the angle between the applied force and the displacement? What is the angle? You see, the displacement of the object is in that direction. So what do you think is the angle between this applied force and the displacement? What is the angle?
Just in the same direction, C0.
No, you didn't hear what, there are two forces at play here. There is a force that the electric field is exerting. That force has been indicated in blue. There is also the force which the external agent is acting such that this force, this charge here moves quasi-statically. That force is indicated in black. This is what we are calling the applied force. Now,
quasi-statically means moving in the opposite direction.
Quasi-statically, we say that it's moving very, very slowly in such a way that it can be considered to be always in equilibrium. So quasi-statically means that it is moving very quasi. What does quasi mean? It means that something that looks like, but it actually isn't, so to speak. Okay, so quasi, it means that it looks like. Static, it means it's not moving. So quasi-statically, it means that this charge is moving very, very slowly in such a way that it can be considered to be always in equilibrium. What does it mean? In equilibrium, it means that the force that is the force that is acting in one direction must be equal to almost equal to the force that is acting in the other direction. Okay. So now this force that is in black here, where is it coming from? It is coming from an external agent. This force in blue is coming from the electric field. So this force in black is what we are calling the applied force. Now, my question is that the object, ultimately the object has to move, to make a movement like this. It has to make a movement like this. So what do you think is the angle between this force, the applied force in black, and the displacement? What is the angle?
180.
The 180. And what is cosine 180? It is -1. So you can see that what is the relationship between the work that is done by the electric field and the work that is done by the external agent? They are negative each other, because here the angle was 0. So cosine of 0 is 1. And then here the angle was 180, and then cosine of 180 is -1. So we see that these are two, they are negatives of each other. Okay. So then what is the relationship between the applied force and this guy? Okay, you see that the applied, since this, we can say that then the work that is done by the applied force must be equal to the minus of this work. You see this work that is here, and which must be equal to the minus. The work is given by minus change in potential energy. So this must actually be equal to the change in potential energy. So the work that is done by this force, which is the applied force, the force that is applied by the external agent, is just equal to the change in potential energy of this charge. Okay. So now what has this got? So this is this potential energy here, which is equivalent to the work that would be done by the external agent when moving. Okay, sorry, we had an interruption in terms of the connectivity, but I think at the point where we had that disturbance, I was talking about the work that is done by the applied force. The relationship between the work done by the applied force is equal to the change in the potential energy of this charge that we are moving. Okay. And then that is what is referred to as the electric potential energy, the electric potential energy. Okay, maybe any questions? Any questions? It's clear. Okay, thank you. So now I have a question for you here, which we have to answer together. So the question says that in the right figure, meaning that in this figure, okay, so in the right figure, we move the proton from point I, which is here, to point F, which is here, in a uniform electric field directed as shown. So the direction of the electric field is in this way. So the question is, which statement of the following is true? Which statement of the following is true? Okay, so I'll give you a minute. We'll go through those options, and then you tell me which statement is true.
In a uniform electric field, the following is true.
Okay, so anyone who has come up with the answer? Anyone who has come up with the answer?
Which statement? Electric field. The electric field does positive work on the proton, and the electric potential energy of the proton increases.
You are saying that the answer is what? Just kindly.
The electric field.
B.
The answer is B. Okay, so that is coming from Madam.
The electric field.
This answer is coming from Madam who?
B.
B. The answer is coming from Madam who?
Elizabeth.
Elizabeth, good. Okay, so now what do others think? What do others think? As others are thinking, Madam Elizabeth, why have you opted for B?
The electric field does negative work on the proton because the displacement of the proton is from I to F, but it's moving in the opposite direction, meaning the angle there is 180.
180.
And if we calculate the work, it's going to be
good. And then what about the other part? So I'm very happy with what the analysis that you're making. So you're saying that the electric field does negative work. Okay. Now what about the other part? How did you work it out about the potential energy? How did you work it out? Okay, please thinking, let me get submissions from others. Okay, if others are not thinking anything, then maybe let us skip this slide, then we'll come back to it later. We'll come back to it when you guys are ready. Okay? If you are ready, then we'll get back to it, okay?
Sir.
Yes, please.
I think the answer is A.
The answer is A. Electric field does positive work on the proton. Okay, why do you say A?
And the electric potential energy of proton increases because there is an increase in terms of the energy. One thing that we need to understand is that the proton is moving. It's not stationary. So it is moving from point I, point F.
What if it was
so
moving? What if it was moving from in this direction? If it was moving to the right, then how would that be different according to your analysis?
Then the sign.
The sign of the what?
You come again, sir?
You know, you have said that since it is moving, then it means that the potential energy will increase. But then if it moved to the right, then also it would be moving. So would the potential energy increase or reduce? I wanted you to say something in that line. If you just say that since it is moving, then the potential energy will increase. Then my question would be, what if it was going to the right? It means that it would also be moving, right? Then what would happen to the potential energy? So I wanted an explanation in that line.
The potential energy will decrease since the
okay. So let us try to do an analysis together. Let us try to do an analysis together. Okay. So option A, it says that the electric field does positive work. Now remember, the formula for work is equal to what? The force times the displacement. In this, let us say the displacement, what was the letter? Delta R. And then cosine theta, where theta is the angle. So the key is here. Okay, so in this case, the electric, in what direction is the force? The force, of course, is in the direction of the electric field. But then the displacement, so what is the angle here? The angle, as Madam Elizabeth had pointed out, theta is 180, definitely. Theta is 180 because the force is in this direction, then the displacement is in this direction. That is the analysis that we are making. So we know that the work that is done by the electric field, you see, this is the electric force. So the work that is done by the electric field will be negative because cos theta will give us -1. Any problem there? Just there before we proceed. Any problem? Are we all together? So it means that just the very first sentence where he says that the work done by the electric field is positive disqualifies that guy. Are we together? Now let us come to option number B. It's not a number, it's just the option B. So electric field does negative work on the proton. So this is correct because, you know, according to the analysis that we have already done. Now let us look at the other part where it says that, and the electric potential energy of the proton decreases. So we want to investigate this decreases. So what is the relationship between the work that is done by the electric field and the potential energy? According to what we have learned from the previous slides, what is the relationship? The work must be equal to what? The work done by the electric field must be equal to what? Negative.
Work is equal to potential.
Negative. This is the work that is done by the electric field. It must be equal to the change in the potential energy. Now, this change in the potential energy, what does it mean? It means when there is a negative change, what does it mean? It means that the initial energy, remember, this means the change means the final minus the initial. Are we together? So what does it mean? It simply means that when you distribute this, it means that you are saying UI minus UF. So it means that the initial potential must be greater than the final potential in order for us to have a negative work. So what was I saying? What was I saying? So is this correct? If the initial is actually less than the final, then has there been an increase or a reduction? Has there been an increase or a decrease? I think I'll try to explain this again just for you to get the picture. I think people have not understood here. Are we okay with this formula here for now?
Yes, sir.
We are okay, right?
Yes.
So this negative, what does it, when there's a negative change? When there's a negative change, it means that the initial is greater than the final. Are we together? Because you remember that change is, okay, just excuse me one moment, just one moment. Okay, so sorry, I just had come in the office. Are we there? So what I was trying to explain is that, when you have a negative change, remember just this change alone is given by the final minus initial. That's what change means. So if the change is negative, what it means is that the final quantity is less than the initial. Are we together? So if the final is less than the initial, can we say that it's a decrease or an increase? If the final is less than the initial, can we say it's an increase or?
It's a decrease.
It's a decrease.
It is a decrease.
Yes.
Okay. Let me explain it. This is quite a notorious concept here. Okay. Trying to understand this negative, that when there's a negative change in the potential energy, okay? When there's a negative change in the potential energy, it means that the initial, this initial is greater than the final. Is that what I said at first? If there's a negative change, in order for this quantity here to be negative, in order for this quantity here to be negative, it means that we are subtracting a bigger number. Excuse me, I think there are people making noise in the background. Let me just mute. Okay, if there's a negative in the change in the quantity, it means that this guy here is greater than this guy, so that when you subtract a smaller number from when you subtract a bigger number from a smaller number, it gives you a negative. So it means that the initial is greater than the final. Now, if the initial is greater than the final, it means that this is the initial, okay? This is the final. It means that there has been a reduction. Are we together? Are we together?
Yes, sir.
So is that the case here? It means that the potential energy has reduced, right?
Yes.
Let us try to consider option number C. Option number C says that our force does positive work on the proton. In what direction is our force? In order for us to move the proton from here, the proton is positively charged. So it means that the electric field is pushing in this direction. So in order for it to move from here, it means that as we are applying a force in this direction. So is this force doing positive or negative work? The force that we are applying. Is it doing positive or negative work?
Negative work.
Doing what?
Positive.
Positive.
Negative work.
It's positive work because the direction of this object is in this direction. The direction of our force is also in this direction. So the force and the displacement are in the same direction. So it means that our force does negative work. So this is correct. What about the other thing? And electric potential energy of the proton increases. The electric potential energy increases. So how about that? Is this sentence correct? No? So have you seen between B and C, the first part is correct. Now we have to scrutinize the second part. Let us go to D. Electric field does negative work on the proton. So this is the wrong because okay, the electric field does negative work on the proton. So this is correct because it's negative. And then the electric potential of the okay, so what is the difference? What is the difference between B and E? What is the difference between B and E?
There's no difference.
Okay, so I think there is no difference there. And then it should be the question as a problem. And then E, it changes in a way that cannot be determined. So this one is automatically not an option. So between the options that we have B, C, and D. B, C, and D. Now, let me explain to you why this B as well as the D are wrong. Let me explain why. You see, when you are actually moving the what? When you're actually moving the proton to the right, we are saying that the external agent or the external agent is actually doing positive work. Okay, now that positive work that you are doing, remember what we said from the work energy theorem, the positive work that you are doing is actually stored as potential energy in that system. So it means that if the energy is stored as potential energy, it means that the potential energy is actually increasing. Are we together? The potential energy is increasing. So I think our answer here should be this one, because we have seen the first aspect of it. The force is actually doing, the force that we are applying is doing a positive work, because the force and the displacement are in the same direction. And again, the proton, the potential energy of the proton will increase. Now, what does that mean? It means that if you move the proton in this direction, when you let go of it, see, it will have the ability to go back on its own. If you let go of it, it will have more ability, remember, to do work on its own, to go back in this direction. It means that its potential energy would have increased. Any questions there? Any questions?
Since you are saying that the angle between the force and the direction of the displacement is 180, how come the work done when the force is positive?
Okay, so you must understand, I think what you have not understood, sir, I don't know, are you the one who is in that noise? Maybe you are in a noisy place. Okay, so what you must understand, there are two things that are happening here. There are two things that are happening here. Let me rub everything. There are two things. There is the electric field, and then there is also our force. The electric field is applying a force. The force is in this direction. So we are saying that the angle between the force due to the electric field and the displacement is in this direction. So let me draw it in a different color. So the displacement is not changing. It is in this direction. So in this case, the electric field is the electric force, and the displacement form an angle of 180 degrees. So it means that the electric field does negative work. Now, what about the force? Our force, it means that the force of the external agent. Since the electric field is exerting a force in this direction, it means that in order for us to move the displacement, to have this object to move in this direction, we must apply a force in this direction. This force is what we are saying our force. So what is the work that is done by our force? Our force, you see, our force is in this direction. Our force is in this direction, which is the same as the direction of the displacement. So what is the angle between our force and the displacement? The theta is equal to 0. It's different from the 180, which is the angle between the force due to the electric field and the displacement. So since the angle is equal to 0, we can say that our force is actually doing positive work. I don't know, I hope that is clear. Is it?
Yes, sir, it's clear. But again, was it supposed to be stated in the question that the work done? Yes.
Pardon? Hello?
The question is just open, it's general.
The question is general.
Yes, so even for B, it can be a correct statement because they're saying that the electric field does negative.
No. For B will not be the answer because, you know, the first part of B is correct. The first part of B is correct because, of course, the electric field will do negative work, but then the potential energy of the proton does not reduce. The potential energy of the proton increases because the work is being done on the proton by moving. The work is being done on the proton by the external agent. So it means that that work that is being done is stored as the potential energy. So the potential energy is increasing. We are going to see at a later point that whenever you have a positive charge move in the opposite direction to that of the electric field, then the potential energy will always increase. When the positive charge moves in the same direction as the electric field, then the potential energy reduces. So the correct answer here is C. Okay, so maybe just try to go, just in the interest of progress, just try to analyze it, try to take some time to analyze it and see, maybe we can come to it, but for the sake of interest, just allow me to move. We have spent too much time there. Okay, so now in terms of equations, how can we calculate? Let us now come to electric potential. We have talked about the electric potential energy. Now let us come to electric potential. So in order for us to understand electric potential, let us still talk about the potential energy. Imagine that you have this test charge. This test charge is moving within an electric field. From the previous discussion, we have said that if the electric, a charge moves in an electric field, the potential energy would either increase or reduce because there is some work that is done. So what is the work that is done? You see, just in moving this charge from I up to F, the initial up to the final position. So you can think this path is subdivided into small paths, all right? Each one has got a length of the S, okay? Each one has got a length of the S. So what is the work that is done just by moving this guy just within a displacement of the S, a small displacement of the S. So the work that is done will just be given by the product of the force and that particular displacement. Now, what is this force? Remember, the charge that you are moving is Q naught. So this force will be given by Q naught times the electric field, and then this dot, the ds that was here. Okay, so in order for us to find the total work that is done from here, remember this dq is just for moving it through this small distance. So in order for us to find the total work that is done for the entire path, then we have to integrate. We have to integrate this expression. When we integrate it on the left, it becomes this. And then when we integrate it on the right, remember this test charge is just a constant, so we can pull it out of the integral. So we're just integrating this from the initial position up to the final position. Okay, so this basically is the work. This is the expression for the work that is done. Now we said that, remember what we said, the work that is done by the electric field must be equal to the negative of the potential energy that is stored. So what does it mean? It means that the potential energy must just be equal to the negative of the work that we have found there, and then it should be given by negative Q naught, and then the integral from the initial position to the final position of the dot product of E and the S. So this expression here will be very, very important for us to remember. This is the expression for the potential energy of a charge that is moved through an electric field. It is just basically minus, this minus here, don't forget it. And then that charge and the integral of the dot product of the electric field and the path that, this is what is called the path integral. Okay, so this is what we have found here is the equation 4. So as long as we know the electric field, we can actually calculate the change in the electric potential. The electric potential energy. Okay. Now, what is electric potential? There is a difference between electric potential energy and electric potential. So the electric potential energy is basically the electric potential is basically the potential energy per unit charge. The electric potential is basically the potential energy per unit charge. In other words, if this, what you had here was a unit charge, then what would be the electric potential? What will be the change in the electric potential energy that it will undergo as it moves from the initial to the final position? So it means that the change in the electric potential will just be given by the change in the potential energy per unit charge. Remember, the change in the electric potential energy is given by this expression. So if you divide it by the charge, this Q naught and the Q naught can cancel out, such that you just remain with this expression that is here. Okay, so we have derived two expressions. The first expression is for the potential energy. You must multiply, it's the negative of the charge and the path integral. And the change in the electric potential is just the negative of the path integral. The path integral is just the integral of the dot product of the electric field and the element of the path that has been taken. Okay, so maybe let us try, before we try to take up an example, let us just try to say something. We say that just as with potential energy, only differences in electric potential are meaningful. So when we are talking about this, when we are talking about potential energy and potential, what we just pay attention to is the difference. So usually what we do is that we have to take a reference. We have to take a reference. Usually what we say is that we take the potential energy to be equal to 0 at infinity. Okay, the electric potential to be 0 at infinity. So now what does that mean? What does that mean? You can think of it let us think of it in this manner. If I have this electric charge, it is the one that is producing the electric field in this direction. So this is the charge. And then it means that because of this electric field, if I have another charge here, it means that there will be work. There will be work that will be done on this charge in order to move it from point A up to point B. There will be work. So this work is basically what you call the potential energy. Now, the work that is done in moving this charge from a certain position up to infinity is what is actually called the absolute potential energy. Okay? And the work that is done per unit charge in moving a charge from a certain position up to infinity is what is called the electric potential.
Can you repeat that again?
Okay, so I'll repeat that again. Maybe allow me to go back. I'm remaining with just slightly under a minute before this session closes. What I'm trying to say is that, remember what we had said. I'm showing you this. There's this charge here, which is producing an electric field, and the electric field is exerting a force, which is doing work on this particular charge. Are we together? So what we actually say is that the work that is done in moving this charge from this position up to infinity, I'll explain infinity when we come back from the break. When we move it from a certain position up to infinity, that work is called the absolute electric potential energy. And the work that is done per unit charge is referred to as the absolute electric potential. Okay, so let's go for the break, and then when we come back, we'll pick it up from there. Let's proceed. I'll rewind a little bit on what we had ended before our time elapsed. So okay, so I'll explain it again. Say that we have this point charge, and then this point charge is actually producing an electric field in this way. So at every given point, there is an electric field. So this is basically the electric field. Okay. Now, if I introduce another point charge within the vicinity, I introduce another point charge within the vicinity of this other point charge. Okay, so if I introduce another point charge, let me call this point charge as Q. It simply means that there will be a force. There will be a force that will be exerted in that direction. So this will be the force, which I can say is the force due to the electric field. Okay, and then what is this force? What is this force? This force will just be given by this, the magnitude of this charge, times the magnitude of this electric field. That is the magnitude of the force. What is the direction? The direction will, since this is a positive charge, the direction will be in the direction of the electric field. Are we together? Now, when this force acts on this, when this force acts on this charge and moves it up to, let us say it moves it up to this point, it means that the electric field has done work. The electric field has done work on this charge by moving it from here to here. And what is that work that has been done? That work that has been done can be work will just be given as the force and the dot product of this force and the displacement. The displacement is basically the distance from here up to here. This is the displacement. Okay. Now, since the angle here is equal to 0, so I can just say that this work is just this, and then times that. Okay. So this work is actually going to be minus the electric potential energy. Okay. So it means that the potential energy will just be equal to minus of the work that is done by the electric field, which is just equal to minus of this. Now, what is Fe? Fe, we have already said that it's minus Q, E, and then delta R. So I'm sure we are all okay with this equation. Now, I'm interested about this delta R. Okay, so now, this electric field, what happens to it as you go away from the charge that is producing that electric field? What happens to the electric field? Does it increase or it reduces?
It reduces.
It reduces. So if you go away far enough, if you go away sufficiently far from this charge, you are going to find that the electric field will be effectively equal to 0 because the distance has, the distance is too much. So because the electric field is reducing as you go further away, at a given point, you can consider that the electric field is effectively equal to 0. Such a point can be considered to be infinity. Are we together? Are we together? So we are saying that the work that you do in moving a charge from a certain position through up to infinity, you remember infinity is the point where the electric field will effectively be 0. So that work that you have done, when this is basically, this displacement is from a certain point up to infinity, that the work that has been done in that way is what is called the absolute electric potential energy. That is the first point. What is the second point? The second, so the potential, the change in potential energy, absolute potential energy, is just given by what? Minus QE, all right? And then the change You remember this delta E must be the final point, which is infinity, and then minus a certain distance that is here. Okay, that is the first aspect. The second aspect is this is the potential energy. Now, what about the electric potential? Remember, electric potential, the change in electric potential is just given by the change in the potential energy per unit charge. Are we together? So if this guy here, if this charge that you are moving was a unit charge, the work that you would do in moving it from this position up to infinity is what is referred to as the change in the electric potential. Is it making a bit of sense now? Is it making some sense?
Yes, sir.
Yes.
Okay. Okay, so now this is what I was trying to explain here. Let me rub it. Okay, so now the SI unit, I'll leave this for you to analyze. The SI unit for electric potential. Remember, electric potential is basically just the work that is done. The electric potential, the change in electric potential is just the change in electric potential is just equal to change in potential energy over. So the electric potential energy is given in joules. This is given in coulombs. So it means that the 1 volt, which is basically the change in potential, is measured. The potential is measured in joules per coulomb because the energy is measured in joules. The charge is measured in coulombs. Okay, so the electric field, you know, the electric field is basically the force per unit charge. Force is measured in newtons. Charge is measured in coulombs. Okay, so if you do some analysis, you see this. If you do some analysis, then you find that 1 Newton per coulomb, the electric field, can also be written in terms of the potential in terms of volts per meter. Okay, can someone tell me how you can do that?
Repeat the question, sir.
Okay, we want to show that the electric field, you know, the electric field is measured in Newton per coulomb. Are we all okay with it?
Yes.
It's measured in Newton per coulomb because of this equation. Now, the same electric field could also be measured in volts per meter. So the question is that how can the units of electric field be volts per meter according to this equation that we have just? Okay, so let us try to do it together. We know that let us start from here. Let us start from here. This guy here, the change in the potential is basically equal to the change in the potential energy per unit charge. Okay, so what is the change? This change is basically just the work, the minus of the work done. Are we all together then? This change in potential is basically just equal to the minus of the work that is done. And then what is the work that is done? The work that is done is basically the force times the distance. We realize that they are in the same direction. So over that, are we together? And then this force, it can be written in terms of, this force can be written in terms of what? Electric field by Q E, I've written the force times that over the Q. Are we together? So this cancels with that. So this implies, remember where I'm coming from? This the change in electric potential will just be equal to E, and then the change in R, and then the change in R. It means that this electric field can actually be given as that over that over okay, so what are the units of this? This is the volt, the volts, the units of the change in potential is the volts. Remember, this is a displacement. The units of displacement is meter. So you can actually write in that way. Are we all clear on that? Are we together, ladies and gentlemen? Huh? Hello? Huh?
Yes, sir, we're together.
Okay. So the other point that we need to take into account is that the electric energy, since the joule is a very big unit, the joule is a very big unit, we usually measure, sometimes we measure energy in electrostatics in terms of electron volts. So basically, 1 electron volt is just, you multiply 1 volt with the electronic charge. Remember, the electronic charge is 1.6 times 10 to the power minus 19 coulombs, and then you multiply it with 1 volt. Remember, 1 volt is just equal to 1 joule per coulomb. So it means that these coulombs can cancel out. Then you have 1 electron volt will just be equal to 1.6 times 10 to the power negative 19 joules. So sometimes we talk about the units of energy in terms of electron volts when we are talking about minute amounts of energy, such as atomic energies and so on and so forth. All right, so let us try to put together what we have done so far. So we say that the electric field lines always point in the direction of decreasing electric potential. So the electric field lines always point in the direction of decreasing electric potential. So it means that where the electric field lines are pointing, it means that the potential is increasing. And then when you go in the opposite direction, the electric potential is decreasing. When you go in the opposite direction, it means that the electric potential is increasing. And the second point, a system consisting of a positive charge and an electric field loses electric potential energy when the charge moves.
We can't get you, sir.
His mic is muted.
Sir, we can't get you.
Can't get you, sir.
Oh, okay. So I'm saying that we are continuing from where we had ended. Are you able to get me now?
Yes, very clear.
Okay, so I was saying that we are saying that a system consisting of a positive charge and an electric field loses electric potential energy when the charge moves in the direction. Remember this point. When the charge moves in the direction of the electric field, it means that there is a loss. It means that there is a loss of the potential energy. And then a system consisting of a negative charge and an electric field gains electric potential energy when the charge moves in the direction of the electric field. So if these are the 2 points to take, if you have a positive charge and it is moving in the direction of the electric field, then you know that in terms of potential, it is actually moving down. It's like initial will be greater than the final. So it is its potential energy will be reducing if it is moving in the direction of the electric field. If it is a negative charge, now try to relate this what we are explaining here to what was in that question. Okay, if it was a negative charge, then it means that it is actually moving down. It means that there is an increase in the potential. Okay, so the other point, very, very important point, is that the potential difference does not depend on the path connecting the potential difference does not depend on the path, connecting the initial and the final position. Remember, the electric potential is basically just connected to the work, is the work done per unit charge. So since the electrostatic field is a conservative field, that is where we started from. It means that the work it does not depend on the work on the path followed. The work does not depend on the path followed. So in this example here, I think this is just an illustration. Imagine that you are moving a positive charge from the initial point to the final point. Remember, this is in the direction of the electric field. So do you expect that the electric potential will reduce or increase? You are moving the positive charge in the direction of the electric field. Do you expect that the electric potential will increase or reduce?
To reduce.
To reduce. That's what we have learned. So it means that the change in the potential, it means that the final potential minus the initial potential must be equal to the minus of this path integral. Remember this equation, the path integral of the electric field and the ds, the path element. This minus, you shouldn't forget it. Now, what is the angle between them? You see that their displacement is in the same direction as the electric field, so the angle between them is equal to 0. So cos 0 is equal to 1. So you just end up with this equation. Okay, so since the electric field is constant, then you can pull this E outside of the integral, then you remain with this. And then what is in the integral, you are just integrating from the initial to the final, this ds. Remember, ds is just this small element here. This is ds. We are integrating it from the initial to the final. Then what you get? What you get is just the distance from here to here, which is d. So the integral of ds is just d, the distance from here up to here. So in short, we are saying that the change in the potential, it will just be equal to E times D if you have moved this charge through a distance of D. Now, here we have followed this path. Now let us try to follow a different Okay, it's like the internet where I am is not very good. Sorry for that. Okay, so what I was saying is that we are trying to demonstrate that the potential difference does not depend on the path taken. So we have taken this direct path from the initial to the final, and we have found that the change in the potential is just C minus E D. Now let us use a different path. We start from the initial point, we go in this direction, and then we move at an angle of 45 degrees, and then we come. So, and see whether we are going to get the same result if this applies. So we say that, first of all, we want to find, yes, please?
So I just wanted to ask on the path we are following. Are we following the direction of we are assuming that we are following the direction of the electric field?
You know, what we are saying is that the electric field is basically, it provides an electrostatic, it provides a conservative field. So a conservative field, what it means, yes, that the work that is done does not depend on the path taken. So whether we take this path or we take this path from here to here and from here to here, then both these paths are the same because the initial and the final points are the same. Is it clear?
Thank you, sir. Yes, sir.
Okay, so now let us try to evaluate this path when we take this path and see the result that we are going to find and see whether it is the same, so that we conclude that the potential does not depend on the path. So what we are going to do is that we just take this portion from here to here. So the final in this case is C, the initial is I. So it means that the difference, the change in the potential will be VF minus VI. It will be equal to, you see this integral, there must be a minus, the integral starting from the initial, which is C, starting from the final, which is C, and then the initial, which is in this case, I think we must say it, sorry, I think we are here. So the change, the final is C, the initial is I. Remember, we are just taking this segment here. Okay, so when we ask ourselves to say, what is the angle between the electric field and the element, and the path element? What is the angle? It's 90 degrees because you can see that the electric field is downward, but then this path, so it's 90 degrees, and you know cos 90 is equal to 0. So it means that moving from here to here does not contribute anything, to the work that is done, and therefore to the potential. Now let us consider this path from here to here. The final here is VF minus the initial I think there is a typo error somehow here. The initial should be VC. So I think this should be C here. This here should be C. Okay, so we are starting from here up to here. Now, the question is that what is the angle between the electric field and the DS? The DS is here. So the angle between them is 45 degrees. So we say cosine of 45. And then the electric field is a constant, and cosine of 45 is a constant. So we can pull them out of the integral. We get this. What do we remain with in the integral? We just remain with DS. So it's like the integral of DS. It means that this DS, we are just adding from here through up to here. So when you evaluate here, that means we are just finding the length from here up to here. So what is this length? Let us use a bit of trigonometry. So we have a triangle that looks like this. We have a triangle that looks like this, where here it is 45 degrees. And this is basically what we are trying to find, which is the distance C up to F. And then the distance from here to here is just basically the D. Okay, so let us use trigonometry. I'm interested in this and this. So which ratio am I going to use? This is the opposite, and then this is the hypotenuse. So it's a sine. So I'll say sine of 45 must be equal to the opposite, which is D, and then the hypotenuse, which is CF. Okay, so remember what I want is to find is this CF, which is the total distance. So it means that CF will just be equal to D over sine 45. So it means that this integral here, I can just write it as D over sine 45. So you can see this. Okay, this is the D over sine 45. This E cos 45 is the one that was already there. Now, if you try to use your calculator, you realize that this cos 45 is just the same as sine 45. Just try that with your calculator. So those can cancel out. And then what you just remain is with minus E and D, which is the same result as we had gotten before. So it doesn't matter whether you have used this path here, or you've gone from there up to there, then from there up to there. As long as the initial and the final are the same, then the electric potential, the change in the electric potential will be the same. Okay, so as we are coming to an end, let us just try to discuss equipotential surfaces. So basically, this is the name. The name equipotential surface is given to any surface consisting of continuous distribution of points having the same electric potential. So equi comes from the word equal. Potential is just the potential that we have discussed. So any continuous surface which have points that are at the same potential is actually called an equipotential surface. All right, so now the key thing is that these equipotential surfaces are always perpendicular to the electric field. So for instance, in this case, let us say that you have an electric field pattern like this. It means that if you draw these lines, have you seen that these lines at all points on these lines, the electric field is at right angles with these lines. So these lines, they represent equipotentials. They represent surfaces where the electric potential is the same. Okay, so now one thing is that when you are moving a charge, when you are moving an electric charge in a potential surface, on a potential surface, the work that you do is equal to 0. You don't do any work. So for instance, if you have to move a charged object from here up to here, then the work that you do is equal to 0. Why? Because you know work is equal to the electric field times the displacement, and then times the cosine of the angle between the two. Now you can see that the electric field is in this direction, but the displacement is in this direction. The angle between them is 90 degrees. So the cosine of 90 degrees will be equal to 0. Therefore, the work that is done is equal to 0. So this is a very important concept, that no work is done by the electric field on a charged particle while moving the particle along an equipotential surface. So with me here, I have a question that maybe we need to answer together. Maybe I can leave this in the interest of time. I'll leave this, this question for you to go and look at it. And then in the next class when we meet, we can discuss it. Or maybe do you want us to discuss it this time, right now? Do you want us to discuss the question right now? Or we discuss it in the next class after you guys?
Yes, sir.
The next class.
We discuss it in the next class. Okay, so let's discuss it in the next class. Just make sure that you remember. Okay, so as we are coming to an end, let us discuss the potential due to a point charge. What is the formula for the electric potential due to a point charge? Remember the point. Electric potential, what does it mean? It means that we set the potential at infinity. Infinity is just a place where the electric field is effectively 0. So we set the potential at infinity as equal to 0. And the initial position, we set the potential is the absolute potential at that particular point. Okay, so let us say that you have this, this charged object that is producing an electric field as shown here. And then you have this charge that you are moving within the electric field of this charged object. Okay, so as before, we know that the change in the electric potential must just be equal to the final minus the initial. Now you must know that if we are talking about the absolute potential, the final is equal to 0, then the initial, this initial will just be equal to the absolute potential. Okay, so the change in the potential is just equal to this integral here. Now we have to ask ourselves, what is the angle between the electric field and the ds? See, we are moving this charge from here way up to infinity. So the displacement is in this direction, the electric field is in this direction, so the angle is equal to 0. So cosine of 0 is equal to 1, so we just remain with E and ds. Now what is ds? ds is just basically a change. You see, from here up to here, the separation distance of the two, we are calling it r. So it means that the ds will just be the same as the dr, because we have chosen r as the variable. Now, what is the electric field at the point r? You see, this r is a variable. So at the point r, what is the electric field? The electric field is that coming from a point charge. The electric field due to a point charge is just 1 over 4 pi epsilon naught, and then q over r squared. Q is the charge of this. So it means that where there is this electric field, you can substitute this formula here. Then where there is this, you substitute 0. Where there is this, you substitute v. Okay, so if you evaluate that, you realize that q over 4 pi epsilon naught, this guy here, is just a constant. So inside, what you just remain is 1 over r squared. So it's the one that you are integrating. What are the limits of this integration? It means that you are starting from r. You are starting when r is equal to r, the starting point, okay, where you are calculating the absolute potential, and then you're actually going to infinity. All right. And then if you evaluate this, I think that you guys know how to evaluate this using first principles, as you like calling it. Me, I like calling it a polynomial integration. Using polynomial integration, go through the steps on your own, then you'll be able to see that it evaluates to that. And you see this negative that is here can cancel with a negative that is there. So you have this as the expression for the electric potential produced at a given point r due to a point charge. Okay, one thing that we can note is that a positively charged particle produces a positive electric potential, and a negatively charged particle produces a negative electric potential. Okay, so I think for today we can end here. For today we can end here, but then I don't know if you guys have these slides. If you don't have the slides, please ask the class rep to remind me immediately after the class so that I send it. And then we need to improve on the speed at which we are moving. So I'll be skipping some slides that we feel that the students can do on their own. Okay, so next time when we meet, make sure that you go through and then you identify places where we need to spend a little bit more time. Okay, any questions before we call it a day? Any questions?
Sir.
Yes, please.
In simple terms, what's the difference between electric potential and the potential charge?
What is the difference between electric potential and potential charge?
Energy. What's the difference between electric potential energy and electric potential?
Okay, so I think I explained that in the course of the lecture. I said that the electric potential is basically the potential energy per unit charge. Okay, so the electric potential is basically the potential energy per unit charge. Now, what does that mean? It means that if the charge that you are moving within the electric field is a unit charge, is a charge with, it has a unit charge, it means that what you calculate there is the electric potential. So in short, in simple terms, I don't know if those terms will be simple enough, but in simple terms, we are saying that the electric potential is the electric potential energy per unit charge.